Hello everyone, this experiment is about FIR filtering in time and frequency domain. In digital signal processing, if the input data sequence is much larger than the length of the filter, we have to adopt different methods to efficiently implement the convolution of the filter and the input data sequence. So again, because the length of input sequence is too large, implementing FFT with a large sequence is very inefficient and time consuming. So we have to break the input data sequence into smaller blocks, and in each case we are going to take the FFT on the smallest, like smaller blocks, and then somehow put those blocks back together to implement the FFT and inverse FFT, and at the end to get the convolution implemented. So one of those methods is called overlap save. Another one is called overlap add method. In both cases of overlap save or overlap add, the long data sequence is broken. So this is our long data sequence. Long data sequence is broken into different blocks. So different blocks, and another block here. And we are going to take FFT and apply FFT to the smaller blocks. So FFT here, and this makes it much more efficient. But before doing that, we have to do some zero paddings. In overlap save method, the zero padding is done at the beginning. So we have to do some zero paddings here for overlap save. So this is the case of overlap save. For the overlap add method, the zero padding is done at the end. So zero padding is done to the end of the block, the smaller blocks. I'm going to extend the overlap save method and to explain it in detail. So provided the block diagram for you, and when you get an idea for overlap save method, you should be able to implement different block diagrams for other methods such as overlap add or any other thing that is asked in the lab manual. So what happens is we have already broken the long data sequence to the smaller blocks. So I'm going to call each block x1, x2, let's say x3. In this case, I have broken only to 3 blocks, but depends on the definition of the problem. You have to break it to much more smaller blocks. So again, I called it x1, x2, x3, and then you have to do the zero padding at the beginning. So each block is gonna have some zero paddings at the beginning. So let's say if the length of block was L, so you broke each block to length of L, then you add m-1 zeros to the beginning of each block. So basically the length of the whole block at each instance is going to be L plus m minus 1, which is our FFT, actually the size of FFT. So then what we do, we are going to take FFT from each block. So the whole block, we are going to take FFT from this block. And then FFT from second block, and finally FFT from the third block. So next step is just to find the filter sequence. So in order to find the filter sequence, let's assume that we already have that sequence, and in the next few minutes I'm going to explain how we get the sequence of edge in Simulink. So for now, assume that we have these two. Since FFT is in frequency domain, and let's say the edge is also in frequency domain, in order to do the convolution, you only need to multiply them together. So you know that the convolution in time means the multiplication in frequency. So we simply multiply edge for all of them. And the same for here, convolution changed to multiplication for all of them. So here we have sequence of y1 which is related to the first block. Here we have sequence of y2 in frequency domain, of course, which is related to this block, and then we have y3 which is the sequence, output sequence in frequency domain for x3 block. So in order to do that, now you need to take the inverse Fourier transform. So this goes to IFFT module. This goes also to IFFT inverse Fourier transform, fast Fourier transform block. So they all go there. And this is going to give us the y1 of n. So now we are back to the time domain. And this is going to give us y2n, but we know that y2n has an overlap with yn. So there is the overlap here. And the reason is that we did the zero padding. So based on the zero padding, we're going to have overlaps between the outputs in the time domain. So same thing, the output here is going to be y3 of n, which again has overlap here. So next thing is how to put y1n, y2n, and y3n together so that the result is going to be yn, which is the convolution of x of n by h of n. So basically we had a long sequence xn, and we had the coefficients of the filter h of n, and then we convolved them together, so they were convolved together, and this is supposed to give us the yn. So the tricky part is just how to remove this duplication of overlapping, and then at the end how to get y of n. So this is called overlap and save method because the zero padding was at the beginning. So next step, I'm going to explain you the parameters, how to find the parameters, and what are the values for different things. We are going to use a 64 point FFT. So 64 point FFT. This means the length of the block that FFT is going to be calculated based on should be 64. So this block has to be length of 64. And then the length of filter, so length of filter is m. And because this experiment is telling you to take the length of filter as 16, so your discrete filter has the length of 16, then this means m is 16. So you have the whole length, which is 64, you have m, which is 16. It shouldn't be hard for you to calculate L, which is going to be the length of a buffer. that you need to configure in Simulink. So in Simulink, basically you calculate and configure the different blocks, and one of the blocks that gives you this breaking down of the long data sequence, the block is called buffer. So basically, if this is ADC, then you have the long data sequence here, and then it goes to a block which is called buffer. It's called the same name in Simulink, and that breaks down or buffers the data into smaller blocks. For the block diagram that we showed you, we had only 3 blocks, but depends on the size of the input. So depends on this size, you may have other blocks as well. So make sure you configure the buffer properly. After you define the buffer, you have to find out how you can do the overlapping. So we have the blocks, the smaller blocks, and you remember for next block we did the zero padding at this area, and now we need to remove this part, not to remove, actually to copy the part. So let's call it x1, which is part of the whole sequence X. So we need to copy x1, which is from the last part of the sequence, and remove this and replace it with the zeros in the zero padded area of the next sequence. So let's say Y is the next sequence, and of course you know that when you keep buffering, the sequence Y is actually the delayed version of X. So every time you buffer from here to here, let's say the length of 64 or 49, 64 is the length of the buffer. So Y would be the delayed version of X. So of course you need first a delay version, a delay block in Simulink to create Y from X after the buffer. And then you need another block in Simulink which is called submetrics. Submetrics. And the role of submetrics block is to copy part of a sequence. So it gets a sequence at the input and it gives you part of that sequence. You have to go to Simulink help and get help from Simulink about the submetrics block to find out how to configure this block so that when you give X as the input, then X1 is going to be the output. One clue that I can give you is that you have to define it from last, because if you double click on the properties of submetrics, it can you can define to say, okay, copy from the beginning, copy from the last. So of course you need to copy from the last part. So I'll leave it to you to configure submetrics block. And after you have X1, then the next part is you have X1, how to merge X1 and Y together to get the whole block. So basically the question is that how X1 is going to be sitting on the zero padded part of the Y. For that one, you need another block in Simulink which is called matrix concatenate. So matrix concatenate is the block that you need in Simulink. Again, I'll leave it to you to configure this block so that the X1 from the previous block is going to be merged with Y and the overlapping is going to happen. The next part in the block diagram that I showed you in like a few minutes before was to take FFT, and Simulink has a block which is called FFT, which takes the FFT from the signal, and FFT is the 64 point FFT, so make sure you configure it for 64 point FFT. And the important part is that when you take FFT from your sequence, let's call it X, and you take FFT from your filter sequence, let's call it H, and you want to multiply them in, of course, frequency domain, you have to make sure that the both outputs of FFT are 64 point. If you do not set the output of the FFT to 64 point, then you cannot multiply them together. That's where most of the errors normally are coming when you compile your model. If the size of FFTs are not matching when you take FFT from the sequence and FFT from the filter. And then again, at the output, you need to take the inverse FFT. And again, Simulink luckily has another block which is called IFFT or inverse FFT. You can configure that to give you the inverse of FFT. Next part is, you remember that we had Y1 and then Y2 and Y3. So output of the frequency domain after inverse FFT, they had overlap. So you have to remove these overlap parts because they are extra. You're basically duplicating the signal Y1, Y2, Y3. So in order to do that, you have to do something that you already did for merging, with the difference that this time you have to basically do the opposite way, the reverse way. It means that you have to remove rather than merge part of the sequence. For that one, again, you can use the same submetrics. So submetrics. And after you use submetrics, you can configure the submetrics block in Simulink to remove part of the overlap sequence. Finally, the last block that you need is the unbuffer block. So you need another block which is called unbuffer. And the role of unbuffer block is just you remember that you were breaking the whole sequence into smaller blocks. Now you have to put the smaller blocks back into each other so to create the large block. And the output of the unbuffer is going to the DAC, and that gives you a signal at the output, and then you can connect that signal to the oscilloscope to be able to see the output. So basically what we do in this experiment is that we basically create a sequence and then we filter the sequence. So you have to see the input, see the output, and we are going to implement a low pass filter. So next part is to show you how to create a filter sequence which is performing a low pass filter in our system in our Simulink model. To find the filter sequence, you have to use FDA tool. So you type FDA tool in MATLAB and the wizard is popping up. So we are going to implement a low pass filter. So make sure the low pass filter is clicked and checked here. FIR filter, so make sure FIR filter is checked. There are different options. I recommend the least squares option. And for this option, you have to define the filter order. You cannot go by minimum order. Lab manual is specifying the length of the filter to be 16. In order to have a length of 16, you have to specify the order equal to 15. So is 1 less than the length. So whatever order that you define here, the length would be the order plus 1. So you have to define 15 here. Make sure the sampling frequency, which by default is popping up as 48,000, set it to 8,000 because this is the sampling frequency we're going to check with. Here, for example, I define 300 to be the pass frequency, and I define 1000, which is 1 kilohertz, basically to be the stop frequency. You don't have to necessarily choose 300 to 1000. You may need to eventually change this number to get the best result, but this is what I'm going to get. For W pass, I keep it to 1, and W stop, I keep it to 0.1, and I'm going to design the filter. So when you design the filter, this is going to be your low pass filter. As you can see, it's passing the frequencies up to almost 1 kilohertz, and then it has considerable attenuation. Of course, you see some ripples, but you see the considerable like attenuation for any frequency above 1 kilohertz. So after you do that, you have to go to File, and you have to go to Export. So choose the option Export, not export to Simulink, just export. And it says export to workspace and export as coefficients because we are looking for the coefficients of filter. Variable name, I'm going to call it H. So I'm going to call it H, and I'm going to say export. The moment that you define export, if I go to the workspace area, you can see that H, which is here, you can see just where the mouse is pointing to. The variable H is created in workspace, and it says 1 by 16 double. So it means that the length of this vector, the sequence, is 16, which is what we were looking for. Of course, you see the minimum maximum, which we don't care at this moment. So this is H, and this is the way that we create the frequency, the filters coefficients. In order to use this one, then you can just look for a block in Simulink which is called from workspace. So the block is called from workspace, and if you choose that block, you need to define the name of the parameter in the workspace. All you need to do is just to use the same name that we use here, which is capital H, or whatever name that you use for your filter sequence, and that would be your block in the Simulink. So this is the way that we created the sequence for a low pass filter, and we exported to a parameter, and then we use that parameter in a block in the Simulink, which we had for overlap and save method, or for any other method that you're supposed to implement it in the in this experiment. So I guess that's all about what you needed for the last experiment, and I wish you luck in your design. Thank you.